Patrick, what's going on?
Nothing much. Just getting ready for class.
Sounds good. Sorry, I'm late, Herman. What happened to the hair was fine when I woke up, and then I probably did this through through uh through sheer mental effort. Trying to deliver the absolute best lecture I can today for you all. Because it is one of the last two lectures. Not that I don't try every lecture, but I mean, I want to end strong. Getting in the season with the elf shirt. How's it going, everybody? I guess
Good.
said he's ready for class. So Herb, that's really a question for you.
Yeah, no, doing good. Yeah. Second to last class, kind of crazy.
What did you say?
Second to last class is kind of crazy to think about already.
Yeah, super crazy. It's actually it's the second to last class you have to go to. I'm gonna have another class Wednesday that's gonna cover things. It's not even a class. It's a lecture. No, it's my TED talk. I'm in class Wednesday covering things that aren't gonna be on the test or anything like that. They're just fun math things that I want to talk about all year. They didn't fit anywhere, and they're kind of more. They're more advanced. But I'm actually going to go into them. It's more just about the ideas. But and I'm very excited for that. But yeah, no, second to last real class. How's the last week shaping up for you guys? I mean, pretty damn exciting, right?
Yeah, I don't know. Like I work full time, so it's kind of like nothing's changing really. It's just a little bit less work on the side.
Yeah. That's true, I guess. Like the way I think about it though is the last, like I think this week, the week of reading day and everything was always my favorite week of class, for all time, because it was like the week where like I always had finals like the next week, like because you could have finals like Friday, but I never did. I always had finals like the next week after this, and so this week was just like this weird like Wednesday, Thursday, Friday off, like getting excited for winter break, which is coming up. Which I mean, I guess you have less work on the side, which is good. But like this week itself wasn't that bad because teachers weren't allowed to have tests. They I mean, you might have homework or whatever, but you get that done by like Wednesday, and then you just get to like you just get to revel in the eye of the hurricane, the calm of the storm, where class is past, finals is coming. But the point is, you're almost done. Anyway, though, anyone have any questions for me? Also, I'm going to get started today. We're going to talk about functions. Okay, then we're going to get started today. And we're going to talk about functions. I wasn't lying when I said that. Let's share screen. God, look how far we've come. There we go. Look how fast that was. Oh, I can fix this. Fixed. Okay, so let us talk about, before we talk about functions, what the real topic today is. We need to talk about power sets, because I totally forgot to cover that last week. We're talking about sets. It's the last little bit of sets. There are so many parts of sets. There's so many different avenues it goes into. And it bums me out because we don't really go that deep into any part of it. We just kind of go into the shallow end. That's okay. This is how you learn things. This is how you start the class. So this is going to be briefly. This is actually in chapter. Nope. We don't have chapters. We don't have chapters, Daniel. This is going to be in section 6.1, and it is power sets. All right. And so to give it a definition, the power set. So the power set is a way that we build a set from the subsets of another set. It sounds really weird. So the powers is the definition. The power set of a set A, so A is a set, is the set of all of the subsets of A. So it sounds confusing. It's the set of all the subsets. And the thing to think about is just that if you think about set theory, which we've been going over so far, you have a set. And the only really things we know to do with that are we can combine them, make new sets, but in terms of like going the other way, just see what's inside of A, like we can combine them to make bigger sets, but to make smaller sets, the only thing we really know how to do is take subsets. And the power set just keeps track of all those subsets, which is kind of an interesting thing. So for example, the power set of the set A, B, 5 is going to be the set of all the subsets of A, B, and 5. So let's see. I mean, what's a subset of A, B, 5? You could have A, right? A itself is a subset. It's a set built from A, B, and 5. You could have B. You could have just a set of 5. All these are subsets. But you can also have AB, right? It's a subset, right? With 2 elements. You could have A5, that's a subset. Or you could have B5. Am I missing any? Or are these all the subsets? That you,
The empty set, right?
the empty set. Actually, that was the second one I was hoping you forget that one. Yeah, the empty set's perfect. We need the empty set just because the empty set, remember, is a subset of everything. I mean, when we write it like this, it kind of makes sense. Like these are all the subsets of 1 element. These are the subsets of 2 elements. What about the subset with 0 elements? That's always the empty set. It's at the intersection of all the power sets. Very interesting. Anyway, though, what else do we have?
You need A, B, and 5, right? The 3 elements.
Exactly. The whole thing. Now, this is a proper subset, but it is a subset. It's a set built from just A, B, and 5. And then we have to put the curly braces on all of this because it's the set of all these things. It's the set of all the subsets. So this is the power set of A, B, and 5. Kind of neat. It's just the set of all the subsets. And one thing you can note here, I'll say note, that the size of this, these bars, we'll go over them like tomorrow more. These bars indicate size. The size of this set is 1, 2, 3, 4, 5, 6, 7, 8. We'll note that for later. That's another one. That's an even easier one. Let's do the power set of, let's see, the set of the matrix 0, 1, 1, 0, and pi. So if we go through, like Herman noted, we're going to need the empty set because we're going to need the set of 0, the subsets of just 0 elements. And if we look at all the subsets with 1 element, we'd have, well, we just have 0, 1, 1, 0, the set of just this guy, or the set of just pi. We also need the set of them together. So these are all of the subsets that you can make from 0, 1, 1, 0, this matrix, and pi. It doesn't even matter if you don't know what a matrix is. The point is it's just an element, it's a thing. And so we need to take the set of these. And then I'll note up here, note the size of this. Equals 1, 2, 3, 4. Any questions on how we got this? Okay, so next, let's go even smaller. Let's look at the power set of just one number, like lucky 13. Uh-oh. You know what blew my mind when I was a kid? That some skyscrapers or like buildings, they don't have a floor 13. I mean, they do. They just label it 14 and they go on like nothing mattered. It still gets me to this day. But anyway, What are the subsets of just 13? What do we got?
Just empty set and 13.
Exactly, Afra. Exactly. Perfect. Same set 13. This is the power sets of the set 13. The set just 13, just here. And we should note that the size of this set equals 2. All right. Now I have a question for you guys. And the question is, how many elements will the set, or will the power set -1, 0, 1 have? If my computer sounds like a cow mooing again, I apologize.
8.
Yes. Why 8, Afra?
2 to the power 3 equals to 8.
Oh, Afra read ahead, it looks like. Yeah, that's true. I'm going to get to that. But more importantly, what I want to look at on the board here is our set of AB5, the power set of that, had 8 elements. And we should notice here that the specific elements we used here, it doesn't matter. Like if we actually looked at the power set of -1, 0, 1, right, we'd have the empty set, and we'd also have -1, we'd have 0, we'd have +1, we have the set -1, 0, -1, 1, 0, 1, -1, 0, 1, like this. But notice this is directly analogous to this set right here. You have the empty set, A goes -1, B goes to 0, 5 goes to 1, AB goes -1, 0, A5 goes -1, 1, B5 goes to 0, 1, A5 goes -0, 1, -1, 0, 1. Like these two are exactly the same. I mean, the elements are named different things, but really, if you look at it, the power set of anything with 3 elements is gonna look basically the same, just relabeling the elements whenever they happen to be. The point being, the math fact, so the math fact is the size of a power set has nothing to do with, has nothing to do with the elements in the underlying set, with the type of elements, I should say. Just the size of the underlying set. Oops. Does that make sense? So every set with 3 elements will have a power set with 8 elements. You see why that matters? Because it has nothing to do, like the fact that this is A, B, and 5, the fact that this is -1, 0, 1, it never came up. It has nothing to do with how we create the subsets. And it's only the structure kind of these sets. It's kind of like I have 5 fingers in this hand and 5 fingers in this hand. So I have 5 + 5, 10 fingers overall. But if I had like 10 markers here and 10 markers here, or 5 markers here and 5 markers here, and I add them, I would have 10 markers. Like the underlying math there was the sign. 5 + 5 = 10. Like the things I was adding doesn't matter. Exact same thing here. Like the particular things you're taking the power set of doesn't matter. It's the structure of how many there are. Any questions on that? Okay. Well, then this leads us. We're gonna go below the glare now. Actually, we'll go above it. This leads us to a very interesting idea, and Afra kind of mentioned it already, and that is, you can notice here the set of one element had a power set of size 2. The set of two elements has a power set of size 4. 3 elements, power set of size 8. You might see a pattern. This is 2 to the 1. This is 2 squared. This is 2 cubed. It seems to be powers of 2. And the question is, why the hell do powers of 2 show up in power sets? Oh, wait, no, that's what I call power sets. Interesting. But the point is, like, why 2? Let's think about it. So, I'll say the fact first, then we'll prove it. So the math fact, let A be a set within elements, then the power set of A will have 2 to the n elements. That's the math fact. And it works here, here, and here, as you can see. But why? So I'll say proof-ish, because it's not like a real proof, it's a proof-ish. Proof-ish. Consider the power set of 1, 2, 3. Because remember, the power set of anything with 3 elements is going to be the same, right? It's going to be analogous, so might as well consider like the easiest one we can think of, and that's 1, 2, 3. They said before, we'll have the empty set, we'll have the set with just 1 in it, the set with just 2, the set with just 3, the set with 1, 2, the set with 1, 3, the set with 2, 3, and the set with 1, 2, and 3, all these. All right. Let's notice what's going on with each of these things. In the empty set, remember, a set, right, just kind of, the definition of a set, we said everything is either in or out. And a subset, right, subsets of 1, 2, 3 are built from 1, 2, and 3. So a subset of 1, 2, and 3 is just a particular set where for 1, 2, and 3, we have to decide, is 1 in or is 1 out? Is 2 in or is 2 out? Is 3 in or is 3 out? So in the empty set, we have that 1 is out, 2 is out, and 3 is out. Right? They're just none of them are in this set. For 1, so just 1, we have 1 in, 2 out, 3 out. For 2, we have 1 out, 2 in, 3 out. For 3, we have 1 out, 2 out, 3 in. For 1, 2, we have 1 in, 2 in, 3 out. 1 in, 2 out, 3 in. 1 out, 2 in, 3 in. 1 in, 2 in, 3 in. Every subset of 1, 2, 3 really just comes down to making a decision about 1, 2, and 3. Is 1 going to be in or out? Is 2 going to be in or out? Is 3 going to be in or out? And notice for any decision we make, 1 in or out, 2 in or out, 3 in or out, it's going to be a subset. Like randomly, if I just choose here, oh, okay, this is what we're going to do. Patrick first, then Herman, then Afra, right? Patrick, you say in or out. Herman, you say in or out. And Afra, you say in or out. You pick one. Are you ready? So Patrick, is 1 going to be in or out?
In.
Herman, is 2 going to be in or out?
Out.
Afra, is 3 going to be in or out?
Out.
So we have 1 in, 2 out, 3 out. That's this set right here. Any combination you guys could have said of 1 being in or out, 2 being in or out, 3 being in or out is going to be some subset. It's clearly going to be a subset of 1, 2, and 3. And every subset of 1, 2, 3 is going to be some combination of this. So the thing to notice is that the number of subsets is just the number of combinations of decisions for here's where I gotta go below the clear. The number of combinations of decisions for 1 in/out, 2 in/out, and 3 in/out. So how many ways can we combine these decisions to form elements? Which equals, notice 1 being in or out, this gives us 2 options. 2 in or out, this gives us 2 options. 3 in or out, we have 2 options, right? Either in or out. So the number of combinations of options we have, decisions we have to make these subsets are, we have 2 here, 2 here, and 2 here. And so if you know anything on combinatorics, it's going to be 2 times 2 times 2, which equals 8 is the number of options. It's the same idea of if you flip a coin, if you flip 3 coins, right? Because they can either be heads or tails, heads, tails, same as in, out, in, out, in, out. If you flip 3 coins, what are the possibilities for what's showing? Like heads, tails, tails, heads. What are the possibilities? Exactly the same thing. What are the possibilities for in, out, in, out, in, out? It's going to be 2 times 2 times 2 equals 8. I'll say that equals 2 cubed. G equals 8. Any questions?
Is it like probability, like finding the number of outcomes?
Yeah, it's exactly like that, Afra. Yeah, so probability, the probability of an event happening is the number of ways it can happen divided by the number of ways anything could happen. And so both of those, the top and the bottom, the number of ways it can happen and the number of ways anything could happen are both, they're called a field of math called combinatorics. It's all about counting. It's about how many possibilities are there. And same thing here. The question is how many possibilities of in-out decisions can I make here? And the answer is going to be 2 cubed. It's going to be 8. So that's how the power of 2 comes in. The power of 2 comes in because, well, we have 2 decisions to make for every element in our set, either in or out. And then you raise to the power n because we have that many decisions to make. You have 3 binary decisions to make. I like this. I think this is cool. I think it was one of those things where it's like, it's not obvious at all why it works at first, but then once you explain it, it becomes really clear. So the point being though, if we had just any number of elements here, like if P was the set, you can see that, if P was the set up to N, then if you think about it, we'd have n binary decisions to make. We'd have psi number of elements in the power set from 1, 2, 3, all the way out to n is number of ways to combine in/out decisions. Because for every element here, we have to decide, is it going to be in the power set or out of the power set? And for every decision we make, that creates another set, like a particular subset. That's how you create subsets, but deciding if one's going to be in or out, two's going to be in or out, three's going to be in or out. So the number of subsets you can make is the number of decisions you can make. So it's a way to combine in and out decisions, which equals, so we have in binary decisions here. So we have 2 times 2 times 2 times 2 in times, which just equals 2 to the n. Good? I think that's fascinating personally. Awesome. And power sets are weird indeed. Notice I should say all of this we just talked about here, all of this is for finite underlying sets. Because clearly, like the power set of the natural numbers, for example, will be infinite. Or the power set for the real numbers will also be infinite. But interestingly enough, the power set of the natural numbers and the real numbers, because they're just things, we could have the set of them. What's this going to be? Oh, this is going to be the empty set, the set of the natural numbers, the set of the natural numbers, the set of the real numbers, and the set of the natural numbers and the set of the real numbers. So it's like the levels here are important. It's like having an array inside an array almost, where it's like it's just treated as an element of the array. But anyway, yeah, so these are clearly going to be infinite, and we'll talk about those later. Anyway, though, interestingly enough, let's talk about one thing real quick about power sets. Let's say we have the set, let's say we have pi e 5, the matrix 1 0 0 1, like that. And we also have, this is A. We also have B is going to equal just E and 5. The question is, what's the relationship between P of A and P of B? Notice here that B is a subset of A. And notice that any subset of B will be a subset of A. Oh, sorry. Yeah, any subset of B will be a subset of A as well. Right? Like the subset of just E will show up in the power set here. The subset of just 5, that'll be a show up in the power set here. The subset of E and 5, that'll be in the power set here. So the answer is P of B will be in P of A. So I guess that math fact is that A inside B implies that P of A is inside P of B. But we can ask a million questions similar to this. Like one question we could ask is, if will the power set of A intersect B equal the power set of A intersect the power set of B? What do you think? Well, remember, to prove this true, if this is true, that would mean the power set of A intersect B will be a subset of this. So this, like this side will contain this side, and this side will contain this side, with a double containment. Let's kind of like start the proof and see how that would go. Let's say, so here, we want to show that PA intersect B is a subset of PA intersect P of B. And so we'll use the element method. So I'll say, let C be any element of PA intersect B. Well, if you're an element of PA intersect B, the power set of A intersect B, that if you're an element of that, that means you're a subset of A intersect B, right? Power set of A intersect B is literally just the subset of A intersect B. So I'll say, thus, by definition of power set, C is a subset of A intersect B. Now here's the question. If C is a subset of A intersect B, what's that mean? That means thus, for all X and C, X is an A intersect B. Right, that's literally what it means for C to be a subset of A intersect B. It means that every element in C is in A intersect B. Why is that important? We're trying to show that C is going to be a subset of A and C is going to be a subset of B. Because if we show that, then C is going to be in the power set of both. But if we start, but it's kind of hard to see, wait, if C is a subset of A intersect B, does that mean C has to be a subset of A? Well, yeah, kind of, right? I mean, if C is a subset of A, if here's your A and here's your B, and C is a subset of A intersect B, that means C is in here somewhere. Well, if C is in here, well, clearly you're a subset of A and you're a subset of B. But the way you can show that is you say, for all X and C, X and A intersect B. Thus, for all X and C, X and A and X and B. Hence, for all X and C, X and A, that means that C is a subset of A and C is a subset of B. Thus, by definition of power set P of C, I'm sorry, no, definition of power set C is an element of, so is in P of A, and C is in P of B. Therefore, C is in the power set of A and intersect the power set of B. Notice the difference between this in symbol and the subset symbol here, right? The subset symbol means C is a subset of A. This symbol means C is in A, because the power set of A, right, the power set of B, these are sets of subsets. So C is literally one of those elements. Whereas A itself, C is not an element in A, but it's a set built from the elements of A, meaning it's a subset. Anyway, any questions on this? We, of course, also have this side to do, but I believe in you guys. I'll say present for you. But the point is, this is how you work with power sets and things like that. Like, there's things you can do with the unions and things you can do with the complements. It gets pretty gray. But there's no questions. We can finally move on to functions, which are the last thing we will cover in this class, the last thing that'll be on your exam. And so let's get after it. Let's talk about functions. So we'll have section 7.1, and maybe we'll diverge into 7.2-ish. And that is functions, which are things I think we've all heard of. We've been talking about them since like middle school, basically. So let's talk about like the middle school definition. The middle school definition of functions goes something like this. It says that a function is something that takes in an input and spits out an output. And it pretty much left it there. And you might have even seen, like, they might have even had a drawing, might have seen a little cartoon where it's like you have a conveyor belt, and then you have like elements like 1, 2, X, they go into the conveyor belt, and then, you know, you might have a function here, like f of x equals x squared, and then what pops out is you'd have like 1 squared, 2 squared, 3 squared. Right? It's a machine that takes in inputs and pops out outputs. It's not wrong. We're going to work with it for now, because it's useful to dip our toes in. So an example of a function would be the one I just named. It would be f of x equals x squared is a function. And let's note I'll use 3. This takes in real inputs and spits out real outputs. And so just spoiler alert here, the takes in real inputs, the thing a function takes in is called its domain. So the inputs of a function are called the domain. So the domain here are real inputs. So it's going to be the real numbers. And it spits out real outputs. And so the general class of things that a function spits out, the general class of things that it outputs are called the codomain. This is also the real numbers in this case. Now, domain, codomain. Some of you might have had red alerts going on here. Go, wait, isn't that the range? Not quite. We'll go over the range in a second. The range are the particular things in the codomain a function hits. Because, for example, fx equals x squared, it's not gonna output any negative numbers, right? Because anything squared is gonna be positive. So the range would just be like all the real numbers greater than or equal to 0. Right? That would be the range. Those are the ones that are hit. But the general class of things that you're outputting to are the real numbers. It makes sense, I'm saying. So we have another example, and that is you can have a function. Let's give it a different name for fun. G that takes in a matrix and spits out AD minus BC. So this takes in a matrix but spits out a number. So this takes in 2 by 2 real valued matrices, or real valued matrix inputs, and spits out real outputs. So in this case, if it takes in 2 by 2 real value matrix inputs, this means the domain is set of 2 by 2 real valued matrices. Which, don't worry if you know what that means. I'm just kind of pointing out that you can have domains that aren't the real numbers. You can have domains that are weird things. The real outputs are the codomain is once again the real numbers. You're spitting out things that are particular class real numbers. By the way, does anyone know what this function is? G? There's a name for it in math. This isn't random. Anyone taking linear algebra? Well, for those of you taking linear algebra, if you're watching online, this is the determinant. This is exactly what the determinant does. This is what the determinant is. And it's for 2 by 2. That would be such a fun Easter egg if you guys are taking linear algebra. Swear. All right, let's do a definition then. So, definition. Now we talked about this. The domain of a function is the set where its inputs come from and then the codomain, and yes, I'm adding a central preposition, deal with it. And the codomain of a function is the set where its outputs go. Generally, that's what it is. That's why the domain here is the real numbers. The codomain is the real numbers. It takes in real inputs, spits out real outputs. That's why the domain here is set of 2 by 2 real value matrices, because those are the things that go into the function. The things that go out are real numbers. And so now we'll mention that the range of a function is the set of elements in the codomain that get hit by the function. And by get hit, I mean there's something you can plug in, there's some input you can plug into the function where it hits that value in the output. That's what it means to be in the range. It's the set of all those values that get hit. So technically, what it means So if f is a function, actually, let's do all the technicalities at once. So I'll say technicals. Technical stuff. So we write a function with a domain of A and codomain. Let's just say right. We write a function with domain A and codomain B like this. And the way you write it is you would say f colon A arrow to B. When you write this, this lets you know that f is a function that takes in inputs of A and outputs things in the class of B. Just like that. Now, the thing is, though, there could be a lot. So, so we're above. So I'll say example. Above we had f goes from fx to x squared. So above f goes from the real numbers to the real numbers. And g goes from 2 by 2 matrices, this set, the real numbers like that. But notice that, there's a lot of functions that go from the real numbers to the real numbers. If you take in calculus, you've seen a lot of them. E to the x, x squared, x cubed, ln of x, like all these things go from the real numbers to the real numbers. So, absolute value of x, I could go on and on. So there's a lot of them. So when you do this, this is just a way to introduce functions. You introduce functions by bringing up, by bringing up where the input is and the codomain is. But to specify what the function actually does, you have to add an extra line. So I'll say the technical way to introduce the function f of x equals x squared is by saying let f from the real numbers to the real numbers by f of x equals x squared. And the technical way to do G, we'd say let f from the set of 2 by 2 matrices to the real numbers by f of A, B, C, D equals AD minus BC. Or actually, we call it G before. So this right off the bat lets you know where the inputs are and the outputs are. And it also, this is where the inputs are and the outputs are, and it tells you exactly how to go from an input to an output. And the reason this is so important is because, this whole f of x equals x squared, we should notice here that we can have a function h let's say let h be a function from the natural numbers to the natural numbers by h of n equals n squared. H is a different function from f. H is defined from the natural numbers to the natural numbers. Note that h of 0.5, for example, is undefined because h is only defined from the natural numbers to the natural numbers. While f of 0.5, well, 0.5 is a real number, and it tells you for any real number, what you do is you square it to get the output. This is going to be 0.5 squared, which is 0.25. So this is why it's so important to define your inputs and your outputs, because it just tells you where you're working with, right? Because this whole fx equals x squared, I mean, technically, should we include the complex numbers? You know what I mean? Like, how do you know what you're playing with here? How do you know what you're dealing with? And this tells you what you're dealing with. Any questions on that? Okay, cool. So, let's go over the range. The range, so I'll say let f from A to B be a function. Let f from A to B be a function, then the range of f, right? I like to capitalize it. The range of f, this is the set of all things that get hit. It's the set of all things in the codomain that get hit by the function. So this is going to be all y in the codomain, which is b in this case, right? We define our inputs are in A, our outputs are in B. It's all y in B, such that there exists an x in the domain such that f of x equals y. This totally captures the idea of being hit by an element in the range, right? Or being hit by an element in the domain. So, yeah. So you are in an element is in the range of f, if and only if, right? There's some x you can plug into f that will get you that number. And so this means the range excludes things in the domain that don't get hit. If you're not in the range, that means that no matter what you plug into A, f of x is, or no matter what you plug into the function, f of that's not going to equal that element. So to do an example, right? Let's say, example, if we have let f be as above from the real numbers to the real numbers, such that f of x equals x squared, then the range of f is going to equal all y in the real numbers, the codomain, such that there exists an x in the real numbers, such that f of x equals y. Which doesn't really tell us much here, but it's going to turn out that that's going to equal the set of all y in R such that y is greater than or equal to 0. Because this function f(x) squared, it's going to be, it's going to hit everything 0 and above. And we could actually prove that. We're running out of time, so maybe we'll do that next time. But the point is you prove that by proving that these two sets are equal. And how you prove sets are equal, you prove they contain each other. So you'd start with an element of y that gets hit and prove it's got to be greater than or equal to 0. and then you have an element greater than or equals 0, and prove it's going to get hit. That's what the range is. It's all the things that get hit. And so I'll do another example real quick. And that is, this will be an interesting one. Let F, or let's say what's a funky letter? Let's just call it G. Let G be a function. It's not going to be this one, it'll be a different one. Let G be a function from the natural numbers, actually, I said the integers, from the integers to the rational numbers by G of n is going to equal n over 2. So G of n is going to equal n over 2. So the question is, the domain Z and the codomain is Q, right? That's the easy guess from the definition. The domain Z codomain is Q. Now the question is, what's the range? So the range of G, by technical definition, is going to be all the Y in Q, such that there exists an n in the domain Z, such that G of n equals Y. But notice this is not going to be every rational number. For example, 1/3 will never be hit. For all n and z, G of n will not equal 1/3. So 1/3 is not in the range. The reason you can see this is true is because if it did work, well then you'd have G of n equal 1/3. Well, G of n just always gets you n over 2. You have n over 2 equals 1/3, meaning if you cross multiply, you get 3n equals 2, which implies that 3 divides 2, and this is a contradiction. This can't happen. The point being, not every element does get hit. So the range is not just all the rational numbers. It's simply all the rational numbers of the form n over 2. Obviously, right? Because this just takes every integer and divides it by 2. And so everything in that range is, so the range is going to be every rational number that can be written as n over 2. Not rocket science, right? Maybe we'll do more at this next time. But before we leave, let's get 3 definitions down that are important, and we'll talk about them more next time too. So all of this we've been doing today has been using what I've been calling the middle school definition. And then next time we'll talk about what I think, or no, it's not just me, well, the more mathematical, broader definition that really gets more to the point. So definitions though. Definitions. A function must be well defined, which means every input, or I'll say each input, corresponds to one output. Not multiple. So for example, if we look at our f of x equals x squared, from the real numbers to the real numbers, if you look at f from the real numbers to the real numbers by f of x equals x squared. If you look at that, any number you plug in, I can tell you what the output's gonna be. You give me 5, the output's gonna be 5 squared. You give me 7, the output's gonna be 7 squared. It's gonna go to one thing in the output. It's not gonna go to multiple, it's gonna go to one thing in the output. An example that would be against this is well defined. And I'll say every input goes to just one output. And it seems stupid until you find out a function is not defined, not well defined. So what if you try to define something like some g from the rational numbers to the real numbers, and you do this by g of a over b equals a plus b. This is not well defined. Is not well defined. Here's the reason why. Because what is the output of g of 0.5? From one perspective, g of 0.5, 0.5 is a rational number. From one perspective, it's going to equal g of 1/2, which should equal, okay, a over b, this should be 1 plus 2, which equals 3. Or this would be the energy, by the way. There we go. But from another perspective, g of 0.5 equals g of 2 over 4, for example, which equals 2 plus 4, which equals 6. Or g of 0.5 could equal g of 13 over 26, which is going to equal 13 plus 26, which is going to equal, what's that, 39. So the point is, this one input, g of 0.5, depending on how you write it as a fraction, will go to infinitely many different outputs. So inputs of 0.5 goes to multiple outputs. So G is not well defined. And is therefore not a function. Because a function has to be well defined like this, because a function has to be, you need to know if you plug in something what the output is, and you just don't know what 0.5 is here. Any questions on that? Hope that makes sense. Again, we'll do a little more of this next time. And then lastly, so that's what well defined is. And then real quick, a function is called injective, or we're going to call it one-to-one, same thing, if every output also corresponds to a unique input. So, for example, here, the function f of x, f from the real numbers to the real numbers by f of x equals x squared is not 1-to-1. Why? Well, because think of the output 4. F of 2 equals 2 squared, which equals 4. F of -2 equals -2 squared, which equals 4. Multiple things in the input go to the same output. Because multiple things, or actually the better way to write it is because one output can be hit by multiple inputs. Example, f of 2 equals 4 and f of -2 equals 4. So the output 4 does not correspond to a unique input. It can correspond to multiple. Whereas though, if you look at a different function, the function g that goes from the natural numbers to the rational numbers by g of n equals n over 2 is 1-to-1. And the reason this is 1-to-1 is because if you look at anything in the codomain, or sorry, if you look at anything in the range, anything that gets hit once. Anything hit is hit just once. And we can prove this by saying that if g of m were to equal g of n, so if these two outputs were to equal each other, then we get that m over 2 equals n over 2. But that just implies multiplying by 2, that implies m equals n. And so what that tells us is that, what that tells us is that if two things equal each other, their inputs have to be the same. So you can't have two things with different outputs equaling each other. We're gonna cover that more next time too. I just want to get the definition out there real quick for your homework. And then lastly, a function is called surjective or onto. S-U-R-J-E-C-T-I-V-E. Surjective or onto if every element of the codomain is hit, i.e. the range equals the codomain. And so, for example, f, the real numbers to the real numbers by f of x equals x squared is not surjective or onto, since it only hits the positives, right? All the negatives don't get hit, so it's not onto. This function doesn't map, it just doesn't go to everything. The function g from z to q by f of n equals n over 2 is also not onto. It's again, not everything is hit. But the function h from, let's call it z to z by h of n equals m plus 1 is onto, since everything in codomain is hit. If you think about it, if you take anything in the codomain here, think of the number 55, for example, well, h of 54 will equal 55. So any number you give me in the codomain, I can plug in a number to output to that number. I can plug in an input to output to that number. And so that means it's onto. Anyway, I'm way over time. I just want to get these definitions out there to help you with your homework if you want to start doing 3 today. And then 4 we have to do after Tuesday, after tomorrow. Sorry for going so over, everybody, but that is class. Any questions? All right, then get out of here. Please, I'm sorry to keep you. Have a good day.
Cool. Thank you.
You're welcome. I think, Patrick, we had business, right?
Yes.
Perfect. So I
Yeah,
will
I'll-
stop recording. Oh, Safa, what's up?
What's up? Thank you,
See you there.
Professor. Peace out.
Hey, peace out.